scientists. Everybody knows them, and I will make no attempt to introduce them. So they're well known to everybody who is reading about quantum technology in India. We have Professor Achanta Venugopal, Director of National Physical Laboratory, Professor Vijay Raghavan from TIFR, Professor Umakant Rapol from IISER Pune, Professor Urvashi Sinha from Raman Research Institute, Professor Arvind from IISER Mohali, and also the Punjabi University, Patiala. He has now taken charge as the Vice Chancellor of that university, and Professor Utpal Roy from IIT Patna. So we have a very distinguished panel of experts. I request you to please come and take your seats. Your host today, the CAMOST, is, in fact, it is a dual host, because IIT Tirupati and IISER Tirupati host the Center for Atomic, Molecular and Optical Sciences and Technologies together. And we have Professor Prasenjit Sen, who has recently taken charge as the Department of Physics Chairman at IISER Tirupati. And Professor Prasenjit will be co-moderating today's discussion. So Professor Prasenjit, please come. And may I request Sambuddha and Shavani to please welcome our distinguished guests with a bouquet of flowers, and we have a small memento for them. Prasenjit, please. And CAMOST, the center, does whatever it does because of outstanding support from the directors of our two institutions, Professor Satyanarayana. So very, and Professor Bhattacharya, Director IISER Tirupati, is unable to join us today, but he conveyed his greetings. We miss him, but he has some urgent work, so he was not able to join. And prior to Professor Bhattacharya took charge of this, Professor Ganesh was in charge, and he also extended very robust support to the center, which is how it has really come up. So let us welcome Professor Satyanarayana as well. Would you like to come and sit on the front? Yeah, you will enjoy the coffee mug. So many thanks to everybody who is making it possible for the center to operate. And most of all, the program coordinators of the center. Arijit runs the center on behalf of IIT Tirupati, and Sunil runs it on behalf of ICER. So Sunil is not here today. He's not well, but he has joined online. So thank you, Sunil and Arijit, for taking care of the center. We will begin the proceedings. May I request Professor Satyanarayana to speak a few words, and then we will start the discussion.
Thank you, Professor Deshmukh. So on behalf of IIT Tirupati, I would like to welcome all the distinguished scientists who have taken the time to come over and participate in this event. More importantly, being two young institutes, right? Both of us started at the same time, same week. Actually, we had a common foundation stone program for IIT Tirupati and IISER Tirupati on March 28, 2015, in the site of IISER Tirupati. Okay, it was actually a foundation stone for three institutions, IISER, IIT, and there's a triple IT at Sri City near Chennai. And then we started our academic programs the same week. We started on August 5th of 2015. I think they launched it around August 8th or so, or August 10th. And we looked at it as a great opportunity that being the only city where you have an IIT and IISER co-located very close to each other, to work together. Of course, people tell me Bhubaneswar has NICER nearby. And from day one, we have been working very closely in taking together, as a new institute, we have so many challenges that we have to, including finding accommodation for our students in the beginning. So, for example, IISER helped us host our students a couple of times when we were running short, and so on. So, we were lucky in the beginning to have some at IIT Tirupati particularly, to have some very senior professors come and guide us. We brought in about 5 senior professors from IIT Madras, IIT Kanpur, IIT Bombay. To initial time, they're 65, they retire, and then we got a permission from the government of India to re-employ them till they're 70. And Professor Deshmukh was one of them who came here to IIT Tirupati to guide us. And they started doing a lot of work. Professor Deshmukh, in fact, was going and teaching at IISER also at IIT Tirupati. And during this period, a number of events were organized based on his initiative and our young colleagues who joined, where he brought in people from TFR, from NPL and other places, even from international, ran a few workshops and so on. And then we realized that we have this critical mass of about 8-9 faculty members between the two institutes who work in the area of AMO sciences and technologies. And, when these experts came down here, they said it's an opportunity. Why don't you guys work together and create a group that will look at the area of AMO science and technologies? Of course, he's been the leader who has been guiding and helping us put together. So the two institutes together, with a number of initiatives, we're creating a number of joint centers to work together, leverage the presence. In fact, the students have the opportunity to take courses across the campuses. Our students can go register for courses there. Their students can come and register. So they have a bigger basket of courses. They have strong science departments. We also have strong science departments in the IIT. So the number of courses available for the students to choose from increases. And we just do a great swap across the two. Because there are some minor challenges, like the credit codes is not the same across campuses. The grades are not exactly, grading system is not exactly the same. But I keep telling them that if you really want to do something, you'll find a way to make it happen. And that's what they did. They did some mapping, and we do that. You'll have to work with timetables when you do these things. Maybe you'll do some courses out of the. There are challenges. In fact, at day first today, we had our Senate. And one of the issues that came up was a challenge in teaching these courses across the two campuses, because of little bit different calendars and so on. But basic point I'm making is, if you really want to make it happen, you'll find a way to make it happen. And that's what we're doing. So, IIT Tirupati and both of us have been growing. We have been lucky to finish off our campus, the first phase campus. What you see now when you came in is we're building a campus of 2 stages. IISER is building the whole campus in 1 stage, but we are doing it in 2 stages. That's how the ministry had given approvals for us. So this is what we call the stage A, and we're going to start stage B, maybe another 6 months to a year once we get the funding approved by the cabinet. So that way we managed to finish whatever is required. And of course, when you start a new institute, the challenge for our young colleagues is setting up their laboratories, setting up all the facilities, right? So unlike an old institution where you walk in and then there is some facilities available, but then here's an opportunity where you build the whole thing, and more importantly, you're able to get the latest equipment because everything we are buying is new. And so we got a reasonably good funding approved on the DPR for equipment and so on. But it takes time to do all this, having to frustrations of doing through procurement process, GEM processes, and all those things. But we have to work within the system that we are working. So the CAMOST is has been making good progress in the sense of bringing in the AMO scientists together. This is the third annual event that's with. It's 3 years since we started. With Arvindo Mitra was the then scientific secretary in the PSA office. We had the launch when he joined online and launched this initiative at that time. And they're doing a lot of activities, and more importantly, it's been an inclusive initiative where they have associate members from other institutions outside, like from IIT Mandi, from IIT Madras, and so on, right? So from that perspective also, it's bringing everyone together. And then being able to bring in, such eminent people working in this area to come down and talk to our students, talk to our faculty, and discuss out of this thing. And as of course, all of us know that we have the big quantum mission that's been announced. We've been waiting for this to roll out. They said it's starting at the last 2 years. Everyone has been waiting, and at least the cabinet approval, all that has come through. But then how are they going to roll out? That's another thing we're waiting for. In fact, day yesterday, I called Mr. Reddy, who's handling this in DST. I said, when is it? When are the way you're going to take it forward, when is it going to be announced? He said it's almost there, another month or 2 and so on. But anyway, what we are looking at from the beginning is together as a group, how do we work closely with the other institutions, leverage their expertise, from established institutions initially, so that we also grow very quickly with them. So from that perspective, thank you very much for coming forward, and let me thank all of you for taking the time to be here. And I'm looking forward to hear the deliberations that are going to happen today. Thank you very much. Yeah.
Thank you, Professor Satyanarayana. We don't have any rigid format for today's panel discussion because these are the experts, and it is a great opportunity for all of us to hear about quantum technologies directly from them. Sometimes it is said that, okay, we are now in the second quantum revolution, and the presence of these 6 panel members over here is evidence enough that India is right there. So they are amongst the leaders contributing to the frontiers of quantum technologies. Like I said, very fortunate to have Professor Prashanjit to conduct the session along with me. So shall we begin? So I have requested some of the students here to look at the time. And maybe after 7 or 8 minutes, they will just signal us. And then we can, so you can invite the first speaker and.
Yeah. Thank you, Professor Deshmukh. And it's a real pleasure to be coordinating this discussion. So we start with Professor Venugopal. If you, in about 7-8 minutes, you can talk about your vision of the future ahead.
Right. Thank you. Thank you, CAMCOST, and for the opportunity to be here. This is my first visit. Right. So to talk about is my own research work. My research group at TFR is still working. We're working on single photon emitters based on metamaterials and either nanodiamonds or quantum dots inside them, and looking at generating directional single photon emitters, which we demonstrated, random number generator. Then we're looking at generating the single photons in orbital angular momentum state so that we can make use of higher degrees of the properties of photons. So at NPL, I kind of got into this SNSPD single photon detector, like superconducting nanowire based, because the project was going nowhere. Being the head of it, like, so it came onto my head to get it done. So we have demonstrated the first basic devices, and we showed the optical response from these the ones which are made at NPL. So before that, like, I had the experience of designing the silicon avalanche photodiodes and silicon photomultipliers, which are CCDs of arrays of silicon APDs. So right now I'm also looking after the sensors activity at NPL. So, and other activity of my research is on light matter interaction, going towards the full quantum regimes, not the non-perturbative regimes, but beyond that. So this is with this background, like, so I'm trying to see where we can integrate together on-chip platforms. So one area which we're looking at is lithium niobate in collaboration with IIT Delhi. So this is something which I'm looking forward to. The project just got sanctioned and we're looking at it. So integrated platforms is something which I'm keenly looking at for the next 3 to 5 years horizon. So that's for the in general, like, so the quantum phenomena or quantum technologies point of view. There's one more thing coming from NPL, like, so I also have to wear the hat of metrology. So metrology, from metrology perspective, like, so there are two things. One is in 2019, the world over, they've accepted all the 7 SI units. The definitions have been made in terms of each of the SI unit is defined in terms of a fundamental constant. Right now, if we want to measure a kilogram, we don't measure compare with a known prototype, but we measure the Planck constant with as high resolution as possible. And then from that, like, so we estimate the mass. So similarly, time, we always know it's in terms of the Rydberg levels, and the length is in terms of the interferometric measurements. So these are all the quantum metrology in the metrology parlance. So then coming to the quantum technologies, metrology also has a big role to play in metrology for quantum technologies. Whatever we're making, whatever we're going, when I say, like, I have a single photon emitter, like, so do I really have it? What are the, I need to quantify it so that, like, there is a quality product which comes out of it. So the metrology is the art of or science of high precision measurements. So it's not just making a device, but making it high quality is something which we should all be focusing at, right? So one example I can give is the quantum Hall resistance using graphene. So this was demonstrated at NPL UK in 2012, but so far there is no single device which is a metrology grade device. So it takes so much of effort to make whatever we make in our lab to be a metrology standard. Right? So this is something which we should be focusing on. Each of us are working on some advanced technologies, advanced measurement techniques. So if we can convert them into primary standards for the country, so this will become accepted world over, then our products can be tested within our country, and these will have global acceptance. For example, NIST has these SRMs, right? So these are the reference materials, standard reference materials. In general term, it's called the certified reference materials. So similar to SRMs of NIST, like so in NPL has a brand name, under the brand name of BNDs, Bharatiya Nirdeshak Dravya, we make a lot of these certified reference materials. So these materials are accepted anywhere. Like, so once we have a National Metrology Institute stamp, like, so we can sell them anywhere as a high quality product, because all our facilities which are at NPL are globally accepted, because we do these inter-comparisons with the rest of the world, right? Over a 3 to 5 year, each of the measurement capabilities which we have in the country is some of the best in the top 10 in the world, right? We only have few measurement capabilities, but each one is one of the best in the world. And this is by inter-comparisons, which we keep continuing. So what I would like to say is that, like, so whatever from the quantum technologies, quantum measurements, quantum techniques, whatever we are developing, if we can make them as primary standards for the country, we can make one copy at NPL, and then that makes, we can be world leaders in it. There are two advantages of it. So whatever technologies we are developing in the country, they'll get global acceptance. It can be a power supply, it can be a complete quantum computer, like whatever it is. Like, so we can test them and quantify it within the country and make it as a global standard. Right? So this is something which we should all be looking at. We do not want to be another China where our quality of the product is questioned. We need to have globally accepted and cherished quality product. So for that, we also need to look at metrology, and this is something which I would like all of you to stress upon. Thank you.
Well, I'll now request Professor Arvind to share his vision about quantum technology.
See, somewhere it was said that we are into the second quantum revolution. I would say we are into the third quantum revolution, because the first quantum revolution was the initial setting up of quantum mechanics, or quantum ideas were being put together in the beginning of 20th century, which became kind of a proper framework within the 25 years of 20th century. Then, of course, the things are not settled. As you know, foundations of quantum mechanics has many open questions, and quantum mechanics has led to our whole way of looking at the world to get transformed, and intuitive ideas about measurements, intuitive ideas about position, all that has to be changed. Even the logic of quantum mechanics is different. However, these were not the most important things that people did after that. And in the second quantum revolution, we went about applying quantum mechanics or quantum ideas to all kinds of things, from atoms to molecules to nuclei, particles, solids, and you name it, we have done that. So that was second quantum revolution. And second quantum revolution generated a large number of technologies, which you see around the semiconductor revolution, or whatever you may want to look at. Most of these technologies are quantum or have impact from quantum ideas. Now, while in 20th century, we call it the quantum century, along with that, the computing by machines also is a 20th century idea. There were 19th century machines could do many things, but nobody thought machines could compute. However, these two threads have gone parallel, and now that they're coming together, and that's what we are calling is the third quantum revolution, which one is seeing that it is happening. Meteorology was being talked about, and now that many people want to give credits, and people talk about 1984 being the beginning of BB84 protocol, I would say that the very well respected paper of Kip Thorne and Caves about detecting gravity waves using interferometers in which you put in quantum light was in some sense the first set of ideas where quantum metrology became important. And that predates the 1984 paper of Bennett and Buzzard on quantum cryptography. So, of course, the quantum cryptography or secure communication is one of the pillars which started in 84. Quantum metrology started even earlier in 81, 82 with these very important papers where you use squeeze light in interferometry. And then in 1990s with the new algorithms coming in, people showed that you could build, if you have quantum algorithms in quantum computers, you could outperform classical computers exponentially. So this is the backdrop. All the three areas are in the backdrop. But then instead of talking about all that in detail, let me tell you that if you ask someone in 2020, when will quantum computers or quantum technologies will really be around? And people would say, maybe never. I mean, Landauer said never. Then people started saying 100 years. But as from the turn of the century, we have moved the next 20 years, the boundary or the end point, the end game that when these technologies will be really around all over to use, that line has been moving closer and closer. So in the beginning of this century, nobody thought that this is very close or within our lifetimes or our careers. But now I think people feel that this is not something which is going to happen 100 years later. You will see most of these things very soon, or you are already seeing quantum technologies in action in many ways in terms of prototypes and crypto systems and all that. So that is where we are. Well, of course, we are starting a bit late in India in terms of putting together our energies. And we are, I mean, it could have been done 20 years ago, 25 years ago. But then you see, this mission has its own importance. And let me tell you that human beings have been around for about 10 lakh years on Earth, the way as species. And most of you know that the brain size of humans has been increasing. So with the brain size increase, your ability to do things increases, as they say. However, in the past 10,000 years, the brain size has been decreasing, but the abilities have been increasing. This is very interesting new research happening in biology. So the answer is that when you have a grammar-based language as an interface, then you don't need one single very big brain to do things. You all know with cluster computers and so on. So human beings learned this long ago to work together by interfacing through grammar-based languages. So all our languages are grammar-based because they're precise. So any mission is that kind of a system in which you want to put together people, institutions, all kinds of other resources and work together as a mission. So that's a very different mode compared to an individual scientist, an individual group, or an individual institution doing things. And I think that if we move in the mission mode in the country, that will lead to very different kind of outcomes. And that's how that should be also envisioned. I want to just say that we have to move with caution because as far as development of technologies are concerned, there could be, I mean, it's great because lots of technologies are going to come up and people are talking about quantum technologies all over the world in a big way. And everyone should maybe jump into it and the mission should develop further. However, one should be realistic. And three areas of caution which I want to mention. First is that we do not really have an ecosystem where technologies or things come out of academia, then there is in academia industry collaboration, then you file patents, then people take those patents and produce technologies and sell them in the market. Somehow we have not managed to do that very successfully in any domain in a big way. So I'm not saying that we cannot, but we must be sensitive to this, that the previous technological revolutions which have changed the world, we have not participated in this way of doing things. So that is the first thing we should be very, very careful about and put it into the mission as it unfolds and be clear about our limitation and lack of industry who would come in a certain way and not come in another way. Second thing, of course, that we are late. Most organized programs in quantum information and quantum technologies started in the first decade of 21st century. People were talking about organized programs in Australia, US, Europe. roughly 20 years ago. So we are roughly 20 years behind. This is an advantage and a disadvantage. Advantage being that we know what people have tried and what they have succeeded and what they have not succeeded in. However, the disadvantage is that we are 20 years behind. We don't have that kind of learning and institutions and manpower or human power and so on, which we will have to develop in this country. Of course, Quest which is the precursor to the mission, is now just ending with the verticals after 3 years. And overall, about 200 to 250 people have been trained to work with quantum technologies in Quest. And I think if Quest is not including everyone, one can imagine another 200 people also are there. So this is roughly the number we have, 400 people or 500 people in the country, not more than that. But we need much bigger ambience, much bigger programs and so on. So being late is the second challenge. And the third challenge is, again, very important, because I feel that any process of knowledge generation, which this one, of course, is finally knowledge generation technologies will come out of knowledge, requires certain permanent policy support. So in Indian institutions, and not just institutions which are academic institutions, even our political system, things change quickly. So certain governments push certain things, certain other governments push certain other things, certain directors push something. So we need to have a commitment from policymakers and institutions that we have to kind of support these activities over a longer period of time, like we have done with the ISRO and atomic energy and so on. Thank you.
Thank you, Arvind. And some of you may not know that many decades ago, several decades ago, when this quantum technology was not a buzzword, Arvind was one of those people in India who worked on foundations of quantum mechanics. And some of those things are now leading to new technologies from a theoretical aspect. So while Arvind was a leading theorist, the next speaker on the panel is a leading experimentalist in quantum aspects of matter. So Professor Urvashi Sinha.
I thought it would be Utpal Roy, according to this list. So I'm speaking now. Good.
Going in this order.
Not an issue. So thank you very much to, to Professor Deshmukh. Actually, he's the one who really, sort of encouraged me to make the car ride, and he has been really pivotal in me actually turning up here. So, and of course, the respective directors and Arijit for this maiden trip to IIT Tirupati, and I'm going to also see the temple. So this has been very nice so far. So thank you. Arvind actually did me a disservice, because I mostly wanted to say most of what you said.
You should tell me what to say.
So then, so this is the common joke that we have. I would like to repeat what the previous speaker has said, and then I go on to the next speaker, but then I wouldn't do that. But the previous speaker did a very good job of actually summarizing a lot of what we would have said. And having said that, I do believe that, one of the things I wanted to bring forth in this discussion is what is it that we have planned in the National Quantum Mission? And, specifically in one or two areas which I particularly am, working on and so on. And of course, I also have this in my mind that I would like to end with sort of words of caution, because I do believe that there are many things we should be wary of. Otherwise, we would not really succeed in this mission. So having said that, there are two areas which I thought I'll highlight. One of them is quantum computing. And of course, Arvind already talked about what it does and so on. And I think the audience is mostly the students who are working in these areas. So we don't want to get into the tutorial mode. But having said that, what is it that we want to do? And of course, the idea is that we want to make quantum computers, quantum computing systems with different kinds of architectures. So Vijay, I'm sure, is going to give us a lot of detail on the superconducting devices and the quantum computing vertical in general, hopefully. Otherwise, we are all, saying the same thing. But then, so I won't talk a lot about how we're going to do all this and so on. But it's superconductors, semiconductors, photons, ions, atoms, neutral atoms. So these are the basic areas in which we are going to build these devices. But we already have the Quest program, as Arvind mentioned, where we have set up a very nice base for what it is that, we might want to take forward in the national mission. So we are not starting from zero per se. Although we are starting 20 years late, we could have been 23 years late. But then thankfully, because of Quest, we have a 3-year headway into what we could be building up on. And so that is something which at least is a very nice thing. But having said that, we hope that, we are allowed to build up on that. And that is something we should wait and watch, because we don't know, having said that, as to how exactly the structure will happen in this mission. So the area which I wanted to really concentrate on would be quantum communications, because that is something I particularly have, played an important role in writing the, the DPR part, with Arvind on the communications side. And so what is quantum communications? Well, I think maybe that is also something you're aware of. It is an area in which we are, bringing in different aspects of quantum mechanics into communications, specifically to have higher security, right? So this is one of the key areas to bring about a paradigm shift in how we think of security by changing how things are done now using mathematical hardness. We change that and use laws of quantum mechanics. So quantum key distribution is precisely that, right? And so the other area is post-quantum cryptography. So something we don't talk about a lot, but we should realize that it's not just quantum key distribution. Post-quantum cryptography is another very important area, which has nothing, it says post-quantum, but it's not like beyond quantum. It's actually classical. And so it is based on mathematical algorithms which do not have a break yet in classical or quantum computing. So that is an alternative area. And so we have promised to work on all this in the mission. But having said that, the main challenge in quantum communications is not about Arvind and me communicating with each other using quantum mechanics, because that's not a very useful exercise beyond a point. So we would like different entities to talk to each other who are really far away from each other. And so the main agenda that we have set forth in the national mission is to have long distance quantum communications between different cities, and going forward between countries, and so on and so forth. So in long distance quantum communications, what are the challenges is a question, because we are, of course, the how I turned up here is because of internet, right? Like, so Arijit has been writing lots of messages on WhatsApp and email successively, and ensuring that we are all here. So this is long distance. So this already works, but then in the quantum domain we have certain things which don't work. Certain laws of quantum mechanics prevent certain natural things to happen, which happen in classical. And so we need to think out of the box on how to increase this distance. And so what we have decided to do in the national mission is work on 3 different areas on increasing the distance. The first one, I would say, is perhaps the easiest one, which is based on a fiber-based network. So we would have, long fibers, and then we would have trusted nodes. And that way we would form a backbone for the country. And so we would have multiple nodes and 2,000 kilometers or so of, this coverage. That's what we are looking at. This is something which, of course, is a little bit, it's not as secure as we would like it to be, because we have to trust these nodes. And so if one of the malicious parties gets hold of one of the nodes, then we have a problem. So the whole thing breaks down there. So that is why there is a little bit of a caveat there, but this is something which we definitely plan to do. Having said that, it's not just about fibers. We want to also do free space quantum communication, because that is, of course, a resource we definitely have, being able to talk to each other by looking at each other. And that is called, line of sight quantum communication. And of course, we know that the Earth is sort of round. And so then beyond a point, we won't see each other, and that becomes a problem. So that is where satellite-based approaches come in. And one of our key areas in the mission is going to be using a satellite to distribute this key between distant ground stations in India. Again, a few thousand kilometers is what we have in mind, and also between different countries, between India and other countries. So this is the idea of satellite-based quantum communication. And the third thing is entanglement distribution-based networks. And so there we are not necessarily talking only about QKD. We are talking about quantum teleportation followed by relays and repeaters, including quantum memories. And so these are the main broad themes. The second thing, Professor Deshmukh mentioned that we should have an idea of where we are in this, so far as our country is concerned. And so this is something I wanted to highlight a little bit. In the fiber network, we have, various organizations which have shown different demonstrations over a few hundred kilometers each, but not more than one node at the moment. And so we want to increase that and go forward. In the satellite-based QKD, of course, ours is the project which started this with RRI and ISRO collaborating on QUEST, which is a different QUEST, quantum experiments with satellite technology. And so we have achieved several ground-based milestones within lab, between buildings, between a stationary source and a moving receiver. So, a satellite moves. So to be able to point to it and track it and acquire data is very difficult. So we have achieved that as well. So these are all various kinds of firsts. And we are now, at a stage where we have a system which works very well with everything in it, optics, optomechanics, synchronization. Now we need to make it smaller and space compatible, then we can fly it under the mission. Similarly, our colleagues, in Ahmedabad, with again an ISRO collaboration, they have been able to, under the QUEST Theme 1, they have also done several ground-based milestones. And the difference being that they are looking at downlink-based QKD, where the source is going to be in the satellite and they're going to distribute the key. We are looking at uplink, where the source is with us and we are going to connect up different, ground stations. So this uplink has not been done globally. So there's a challenge, but it gives us a lot of scientific scope. And the third thing is entanglement distribution. So we ourselves are working on quantum teleportation. And of course, people like, Arijit and others, there are many groups who are working on different aspects of quantum memories, right? So the idea under the mission would be to bring all of us under one umbrella so that we can form this network. So I do my entanglement distribution, bring in his memory, his quantum memory, hopefully, and then we can actually do this distribution. So this is what we want to do, and this is where we are. Then, of course, as I said that, I'll echo Arvind, but I have slightly different points in my mind regarding what the problems are, because there's no point in actually just thinking that everything is fine, which is a false notion, right? So the first thing, of course, I do believe is, that we don't have a very nice career pathway for the students who are getting trained in this topic. So of course, they can go into academia, that's one thing, but that is not everything. We also need to absorb them in the corporate sector. And so unlike other countries where, the big industries, they are investing in quantum, in ours, the same Indian counterparts of those industries, they're sitting on the fence, right? And they are waiting for the National Quantum Mission to take money from the mission rather than actually invest in it. And so then we have a problem there. So we want to address that problem, hopefully, so that we don't have people just scatter away. We want them with us as a workforce, these 500 people and beyond, right? The second thing is, of course, hype. Our field, unfortunately, suffers from a lot of hype. And so there's a lot that we can do in quantum, and there's a lot that we can't do in quantum. And so then we have a problem because, sometimes just for instant gratification, people are actually overclaiming. And then, if that falls flat, then of course we end up with negativity. And then Vijay and I don't have any funding going forward because, we have overpromised and not been able to deliver. So that is a big issue, right? And then of course, students, join, so startups, some of them are good, some of them are not. And so, if you're joining and then in 1 year, you don't have a job. So then there is a lot of this happening as well. And the final thing is, we love, making things in India, which is exceptional. And we would like to continue doing that. But at the same time, we have to realize that we are not there yet. So if, Arijit wants to start a lab and he has to import something and he has to wait 3 years for the thing to turn up because we don't have an Indian equivalent, to think of ways of circumventing that, because we need to first be able to make something and then use it. No? We can't use something which is not existing. And so we do have this sort of a chicken and egg problem going on. The last thing I want to say is that, while we are very proud that we are making so many things here and we want the Indian mission to succeed, we have to realize, as Arvind mentioned, that we are 20 years behind, if I were to quote him. So there are many other more mature, programs that exist. So what would be good for us is if we actually were able to collaborate with them rather than, reinvent the wheel because we have to. So international collaboration is very important for us to actually succeed because science is global. And this is something which we shouldn't have any misplaced notions about some misplaced sense of, patriotism. That doesn't help because, we want to do the science. So let us do it together and proceed as a one world scenario. So thank you very much.
Thank you for Nice and very realistic perspective on the possible communication technologies that are possible in the near future. So our next speaker on the panel is Professor Utpal Roy.
Yeah,
Please.
thank you. Thank you very much, all CAMOST members, including Rijit and Professor Deshmukh, for giving me this opportunity to speak here. So I'm actually thankful to the previous panel members. They have included most of the important points. And but I'll be able to get into the things, little bit technical things very quickly within these 8 minutes. So as you know that quantum technology has broader categories like quantum computation, quantum sensing, quantum communication, quantum security, and there are different systems which have emerged for implementation of quantum computations. Superconducting qubits will be coming to know from him and the panel member. And recently IBM has announced the target of 10 to the power 5 qubits in coming 10 years with collaborations of University of Chicago and University of Tokyo. So globally it is in a kind of really a revolution stage. And when it comes, and there are different companies, of course, leading companies are like IBM, Google, IQM. So they are actually taking care of superconducting quantum computers. When you think about photonic based computations, information is basically carried by light, and qubit is encoded in the state of the light. And there are also companies like Xanadu, who takes care of using the squeeze state of light, multimode squeeze states. Then the cold and ultra cold atom quantum computer. This has a lot of advantages. I'll mention some of them. So one advantage is that they are comprising of neutral atoms. So they can be packed in a very small place, and which actually allows you to have a very small processor and increasing the scalability of the computation. Then you have basically the tuning capability of the system is a highly tunable system, and you can actually control by electric and magnetic fields. So that actually helps you to have reduce the complexity. Then you can have a long coherence time. So it is a highly coherent object and having a very long coherence time, long lifetime. And if you can properly prepare ultra cold atom in a state of soliton, you can have lifetime up to minutes. So imagine that a macroscopic quantum object is surviving up to minutes. That's really remarkable. So these are the advantages, prime advantages, that to have the quantum computation with ultra cold atoms. And there are definitely, ion trapped computer, quantum dot, then molecular quantum computations, where you actually couple the vibrational rotational degrees of freedom, and then you can read out the qubits by coherent control mechanism. So these are the quantum computation aspects. Then quantum precision measurements already have basically elaborately said by Professor Achanta, and quantum communication is already described, and security as well. So I'll get into some of the aspects which you focus in my group, and there are similar possibilities in theoretical model in practical systems. So I think there's a large amount of theory is required in practical systems, not theory over theory. So first, in the aspect of quantum computation, the ongoing project from Government of India, which deals with the quantum computations with trapped ultra cold atoms, where actually we have 4 proposals. So one is that a double well potential, where the minimas are 0 and 1, which is actually experimentally already demonstrated, but there's no theoretical model. So a theoretical model will make it more versatile for sure. And we have a triple well model, where presence and absence of atoms in the central well will define 0 and 1. Then we have optical lattice environment, which is a best quantum simulation environment existing, which can mimic the condensed matter system like honeycomb lattice, Kagom lattice, the material like graphene, twisted graphene, and so on. So this system is a kind of prime candidate for kind of a localized state like Anderson localized state. So can be used as a qubit as well. And the last option which we proposed is BC in a chip, but that chip actually this kind of experiment was done several years back. But then if you control the chip in a ring shape waveguide, then actually what happens that by engineering the trap, the cloud actually disperses, but then it comes back. So that is called the revival. And not only revival, there is something more happening in between the revivals. So they are called fractional revivals. So these phenomena are actually recently reported by us in the first time in this system. So which will help you to have a completely dispersive system. You can get the things back and have a qubit operation over there. So that is another promising system, the ring waveguide. And more than that, you can actually have imprint more than one qubit in the same system by imprinting phases. So this is the aspects of quantum computations. Then I'll also mention the activities which are possible for quantum sensing. So definitely a ring waveguide, which I just mentioned, and routinely done in experiments as well in India and abroad. So that can be used as a gravimeter. Basically, what you do is you tilt the optical ring, as a waveguide, optical waveguide, and then you tilt it, and then you observe the interference pattern. And from that pattern, you can actually have the measurements of gravitational constant. And so this is one thing. Second thing is that you all know that optical beam splitter is very well known to all of you. Is a classical beam splitter, but then the system, ultracold atom, is also behaving like atom lasers. So, so it is expected that it will also, kind of show some signature of atom beam splitter. So there are experiments of that. So actually you can have a balanced beam splitter, you can have imbalanced beam splitter. What you use is balanced beam splitter to have precision measurements. You have tiny interference structures which can actually measure not only position, momentum, phase. We have indirect measurements of temperature in the level of precision picokelvin. So which is the highest level of precision achieved so far for measuring temperature indirectly. Then definitely I'll not get into details of the other protocols, like we have reported strong and weak measurements in BEC, trapped BEC, and higher harmonic generation in dipolar interaction in BEC. So this kind of system like dipolar interaction in ultracold atoms is a very promising directions. There are a lot of new phenomena coming on, and they have been used in quantum technologies. Okay, and then another aspect of precision measurements is in cavity quantum electrodynamics, which is actually we use the experimental setup, which is by Professor Sergei Haros, is a Nobel laureate in 2012. So there are two cavities, and there are 3 Ramsey interferometers in between. Then you send the atom through it. So and the initial state of the cavities are actually coherent states. Then you have a lot of tuning parameters. You have initial state of the atom, you have the phases of Ramsey interferometer and the cavities. So this richness of the system allows you to have a lot of non-trivial entangled states, which are highly sensitive in quantum domain. So this is in cavity QED. Then I'll mention briefly, I'll take 2-3 minutes, that for communications that you have arbitrary waves form generations in classical optics, but there's no approach of such thing in quantum physics. You can actually have arbitrary waveform generation in ultracold atom to have different kind of waves. So that also is another directions we have been proposing for that. And then the spontaneous parametric down conversion, which is a prime process for making the things entangled, beam entangled, where you can actually, one can study a truncated non-diffracting array beam. We are giving theoretical model on that. So these are all like these themes, and over and above, I mentioned that quantum information processing and algorithm is very much important. So in that direction, India, US had as recent MOU on advanced quantum computing and AI. So which says that AI can help quantum computation. At the same time, quantum computation can help AI. And all of you know that quantum machine learning is the integral part of AI when you talk about in quantum domain. So you desperately need a good quantum machine learning algorithms, which are not very easy to devise, but then that is required. So we are providing some of the quantum optical architectures for scanning images, clustering problems, and working with the kernels like squeeze state, like the company Xanadu is taking care of that. So these are more or less, the overview of these themes. So I'll conclude with the comment that, the quantum technology will take the height, if we have emphasize on all the broad areas simultaneously. And definitely there must be some coherent ecosystem between the researches of theory and experiment. Thank you.
Thank you, Professor Rai, for giving an overview of various possibilities in this domain. And Professor Rai did talk about ultra cold atoms, and our next speaker is an expert on that. So, Professor Umakant Rapport.
Yeah. First of all, I would like to thank the organizers, Professor Satyanarayana, Professor Deshmukh, and other members of CAMOST for inviting me here to give my perspective on the quantum technologies. Okay, I mean, the earlier speakers spoke quite a bit about various things related to quantum technologies. So maybe I'll just add a few more things which they may have covered or not. So if you look at the combination of the word quantum and technologies, what we are basically trying to do at the moment is, okay, I mean, there was quantum mechanics went through various phases. I mean, through the invention and through first revolution, maybe we are into second/third revolution, as Arvind said. What are we into? What is the age that we are into now? So, I mean, everybody knows what quantum mechanics is at the moment. At least all the quantum mechanics that works in real life, we know to a large extent how it works and what happens when we try to interrogate into various systems, physical systems, how they work at the atomistic scale. Now, we are into an era where we are not using quantum mechanical systems as they are. We are into an era where we are actually playing with the proper basic quantum mechanical properties. We are engineering basic quantum mechanical properties in either photons, atoms. When I say atoms, it could be natural atoms or artificial atoms, mesoscopic systems, etc., where we are actually engineering and manipulating basic quantum mechanical phenomena like superpositions, entanglements, the wave particle duality nature, and tunneling characteristics, etc., in such a manner that we actually are trying to build systems and useful devices which work in real life at mesoscopic scales, where they are going to beat the so-called classical limit. When we say classical limit, we are talking about systems where it's a collective, how should I describe that? I mean, when many quantum mechanical systems come together, like in a solid or something, you enter into the so-called classical world, where the details of what happens at the quantum mechanical level are lost, and you kind of can apply basically Newton's laws of motions essentially and figure out what's going to happen. But that leads to certain limitations in how well we can measure certain things, how well we can use certain things for surpassing what we already know. So one of the examples is this beating the sensitivity limits. When you use light to detect something, as you keep decreasing the light, for example, on the cell phone, you keep decreasing the light, the images become grainier and grainier. Why? Because you are starting to see the photon shot noise. Because the electromagnetic field, when you start attenuating it a lot, you start seeing the granular nature of that, and then that leads to certain noise which changes with time. And that, but if you want to, it has certain characteristics. Now if you want to be more sensitive, what do you have to do? You have to use things like squeezing of the electromagnetic field, which will then allow you to depending on whether you are measuring the intensity or whether you are measuring the phase of the light, you can actually increase the sensitivity by a factor that depends upon how much you do the squeezing along what axis. Anyway, so this is the era that where we are in now. I myself basically use atoms and interaction of photons with atoms, natural atoms, for across various verticals in quantum technology. So I have programs which are running in quantum sensing, in quantum computing, and quantum metrology. So basically, I have one program where I use extremely cold atoms, where they are, where they are put into a state, quantum state, where they all behave collectively together like a single large atom. We take it into a Bose-condensed state and use it as a giant matter wave to do sensitive interferometry using matter waves. So that's atom interferometry, which currently we have demonstrated it for measuring. We did a technology demonstration. It's not anything new, but just used it as a technology demonstrator for measuring local gravitational acceleration to like up to 7th decimal place. Now, this kind of systems when we are talking about technology, it's about translating this into some useful device. So that is an example of a gravimeter, which we are now working towards making a useful transportable device, and which can be taken on the field, and one can do gravity surveys, do hydrological mapping, underground mapping of the hydrology. Or you can do underground resource mapping, various minerals, etc. So that's one application. And this application has been around for over a decade. So across the globe, even before this quantum technology started becoming a buzzword in India or some other countries, people in this field have been working on these things for over many decades now. Only now this has become a buzzword, but so that's one of the applications. Now, other program that we are running is on atomic clocks, optical atomic clocks, where you basically use again a quantum mechanical system, like an atom, two levels in an atom, as your reference oscillator with a very high quality factor. Like, just to compare it with the quartz oscillator that's used in wristwatches, it operates at 32 kilohertz with, I don't know what's the quality factor, but it loses a few seconds every day. Now, we are talking about a reference oscillator, which will not even lose 1 second in the entire age of the universe. So we are talking about instabilities in the range of 10 to the power minus 19 to minus 20, or 1 part in 10 to the power minus 19 to 10 to the power 20. So that's essentially you are using a quantum mechanical system, interrogating the different levels in a quantum mechanical system to measure frequencies very, very accurately. And these oscillators, natural oscillators, have extremely high quality factors, which are used as your standards for time or many other things, which Professor Gopal just some time ago said. So that's one program which is running. And the other program is, again, of course, we are building a quantum computing platform with two different systems. One is for a gate-based quantum computer that is using trapped ions, and another one is for doing quantum simulations, an analog quantum computer, you can say, where you can execute certain problems, solve certain real-life problems, choosing an analogous problem. So basically, you map a Hamiltonian of the real-life system into an analogous Hamiltonian, which can be executed on an array of atoms. Okay, so you don't have to actually run through a complete algorithm and a code where you have a sequence of gates, but instead you kind of try to solve the minima of a particular system and find the find your answer. So that's the analog quantum computer. So there are two programs going on in my group, and what I see is that in any of these areas where I am working on, which have a huge potential for developing something useful, I think there are a good number of people across the country who, some of them are maybe a decade or more old, who have set up these experiments, and some are just starting up. I think there has to be a good synergy that needs to be built. Everybody has to come together because the community is small and the amount of expertise that's there, I mean, the numbers are small, expertise is there, but if we have to boost the efforts, especially for the national mission, I think all of us, there has to be a mechanism or some vehicle through which we all can come together and work without the feeling of competition, but to exchange ideas, exchange resources, students, human resources, everything. Because many of the things, when my young colleagues and friends start, they are actually struggling to build certain things. Okay, they know how to build, but then there are new challenges when we are setting up labs. As a student, when we are working in the labs which are already set up, or when we are a postdoc who is working in very well established labs in developed countries, these challenges we never see. But here, when we are setting up these experiments, we see huge challenges, and especially for our field where it involves controlling atoms and photons, I think there is a lot of support, knowledge exchange, everything is needed for this kind of thing. I think for the mission to succeed, especially in this community of AMO physics, there has to be a much close, what do you call this thing? Yeah, I think I see.
Thank you very much. The final speaker on the panel is Professor Vijay Raghavan. Please.
Thank you. Let me first thank Professor Deshmukh and Arijit for inviting me, and also to the director of IIT for having us here for this event. I'll try and add things which have not been said. So I'm going to give you a very quick overview of the status of building quantum computing hardware in the country, and then what I see as challenges and opportunities in the National Quantum Mission, and just going forward in this field of quantum technologies. So the basic idea behind building a quantum computing hardware is you need some physical system where you can encode two quantum states. And because they are quantum states, you can create superpositions, and then extending it to multiple qubits, you can create entangled states. That's essentially what you need. And there are various ways you can do that. The choice of the system, you already heard, you can do it with photons, you can do it with trapped ions, you can do it with atoms. Umakant also mentioned artificial atoms, and that's one of the areas I work in with superconducting circuits. These are actually electronic circuits which operate at very low temperatures, but under the right conditions, they show two quantized levels. And very simply speaking, they're actually just oscillators. If the oscillator is in the quantum ground state, we call that 0. If it is oscillating with just the minimum amount, 1 quanta of excitation, then that's the quantum state 1. That's one of the simplest qubit you can make using superconducting circuits. And all of these physical platforms have their own advantages and disadvantages. And that basically boils down to how difficult is the physical system itself to control. One can imagine, you would think that atoms are very small, so it's difficult to handle, but over the years, these techniques have been mastered. Because of their small size, atoms and ions also tend to interact less with their environment. And it's sort of natural that one needs quantum mechanics to describe the properties of atoms. So if you're using it to make a quantum system, it should be a good quantum system. And that's one of the big advantages of using atoms and ions, as opposed to superconducting circuits, which are actually made on a chip. And they are millions of times bigger in size. You can even see them with your naked eye. And yet, under the right conditions, they show these quantum mechanical effects of quantum superposition and entanglement. So they have this advantage that they're much bigger, so they're more accessible. They are fabricated using mostly conventional techniques. So you can imagine making a chip with thousands or millions of qubits, just like you can make a semiconductor chip with billions of transistors. But because of their large size, they also interact with their environment a lot more strongly, which has both pros and cons. The con being that it tends to lose their quantumness faster compared to ions or photons or trapped ions. But there's an advantage that you can now control them and change them faster because interact strongly with the field with which you are doing. And that's also important because in general, if you isolate the quantum system very well, it behaves nicely as a quantum system. But if you isolate it so much that you cannot do anything with it, because a quantum computer requires you to control and change and make it behave the way your algorithm wants it to go, you have to do it faster. So in that sense, the ion traps and superconducting circuits, which are currently considered the two leading platforms, ion traps they can survive a lot longer, but they also respond very slowly. Whereas superconducting qubits don't survive that long, but they respond much faster. And it's the ratio of these two time scales which ultimately matters on how useful it is. And I think they have similar metrics on that front. So that's sort of the quick intro there. What is happening in the country? Umakant already told you they are working on an ion trap based system. There are also electron spin based qubits which are being worked at in a few labs. Photon based qubits are also being worked at, and I think recently a lab in IISc showed up to 2 qubits. I think Urvashi's group also has done some experiments with photons on qubits, but superconducting qubits, which was first, I would say, modern lab set up in the last 10 years in the country. Ours was the first one. We have a published result with 3 qubits as a completely new design. We kind of reimagined what a superconducting qubit can be, in the sense that it was not 3 individual qubits, which is typically the strategy. It was a single circuit which manifested itself as 3 qubits. And then we are now working on a 7-qubit project with DRDO and TCS, where we are actually trying to put together a full system. And it can be operated and accessed by anyone once we launch it. And currently we have tested up to 4 qubits in that experiment. Apart from photons and superconducting qubits, none of the other platforms in the country have yet demonstrated a single qubit experiment as well, because these experiments only started very recently. All of these require a lot of investment, and that has only happened in the last 10 years and much more aggressively in the last 3 to 5 years. So that's kind of the status. Coming back to the challenges, let me first say that the National Quantum Mission is an unprecedented opportunity. I think we have not seen this kind of funding being promised for anything in the recent past. So it does present us a unique and amazing opportunity to really do something. But many of the important challenges were highlighted by Arvind and later on Urvashi, that we are starting late. But I would add there that we are not late enough in the sense that many of the challenges for turning this into a real technology have to be still solved. And if we do the right things, invest in the right way, and organize ourselves correctly, those breakthroughs can happen here, and we can take a leading role. But there are challenges. So the fact that we don't have the 20 years of basic research, which means that we now have to do both of them at the same time. We need to be able to focus or give enough focus to cutting edge blue sky research where new ideas can emerge. At the same time, we have to put together the teams which will start building systems based on existing knowledges. Now, this comes with its own caveat, is that these kind of engineering projects are not very suitable for an academic environment or for a PhD student because it's already been done. So you need to find the right team, maybe engineers from government labs who are not looking for a publication or for a thesis, working together with the PhD students and the academic experts who are also trying to push the boundary. And that's going to be a unique balancing act we have to do because of the fact that we are now embarking on such a massive program with very little preparation compared to what has happened, say, in other big countries in the West. So I think that's sort of what I wanted to say. One last thing is there are actually many aspects of actually developing practical quantum technologies which have nothing to do with quantum mechanics. A real quantum computer at the end of the day is going to be 99% or more classical high-end electronics. So we actually need a lot of engineers, many of whom in the country have the necessary expertise and skill. They actually just don't know yet that their expertise is relevant to this technology. So this also is something we have to do. We have to leverage all that and bring them together to put those systems together. Because at the end of the day, the quantum part, if you think about the ion trap, it's only the atoms and maybe the light, which is quantum. Everything else is classical. And a quantum computer has to interface with the classical world. So you need a lot of that stuff going on. But these are all very precision, high-end, high-speed electronics and optical systems. But for that, we do have the expertise. We just have to bring them together. So I'll end with that. Thanks.
Thank you, Professor Vijay Raghavan. So with that, we come to the first round of this panel discussion. So the panelists have exposed us to some of the cutting edge ideas, the experiments taking place in their labs, and the technologies they can potentially lead to. So I'm sure there would be more questions, but I'll hand over the mic to Professor Deshmukh to take care of that.
We can continue in a very informal manner. We can have questions from the audience, but the panelists can also ask questions to each other. That will also be very interesting for the audience to listen to the conversation between experts, because that kind of an opportunity is very rare for the audience. And this is a tremendous opportunity for everybody over here, because between the 6 experts who you just heard in the presentation of each, there was so much of experience which was communicated to the rest of us. So it's going to take us some time to really assimilate what you said in these 7 or 8 minutes, to really grasp it, because it was very dense, and really enjoyed it, very excited by the comments that you made. Let me just begin this by asking a question. Arvind, you mentioned that sometimes starting late can also be an advantage, because you know what to do and what not to do from the mistakes that others may have made. My worry is, do we really learn from this, from the mistakes that others make? We usually learn from our own mistakes, if at all we do.
The reason I said that was I did not want to sound too negative. Because we are quite late. I mean, I tell you, we did a workshop on quantum ideas in Mysore in the year 2000. And my duty was to review the superconducting ideas, which I read up the papers and reviewed. That was year 2000. And the superconductivity ambience in this country has been there because we had the superconductivity mission. So what was the difficulty in having our superconducting experimentalists begin to brainstorm around such ideas? Nothing happened. Then the nano mission came up. Nano mission came up again in those years. That was 1100 crores. So it's not that we have not funded. 1100 crores 20 years ago was not very different from what you are talking about now. This is just 6 times 6,000 crores. So all what some of us were proposing was that make a seed within nano mission called quantum ideas, and give 50-60 crores and set up one center, maybe in Bangalore or somewhere within the nano mission, or whichever way. That was also year 2000. So what I mean to say is that on the other hand, one should also not say that we are that late, because in these 20 years, the groups have been working. You see, groups in the country have been working, just that we couldn't really leverage it into a bigger activity because we could not do organized funding and activities. So, well, people have not been sitting silent, on, and groups develop. But I tell you, see, if you really want to have a realistic discussion, why these things did not happen? Simple reason is that we did not have in the community of people looking at quantum ideas, very senior, well-established people who could, who actually controlled the science. So that was the single reason, I would say. If we would have got a very senior scientist at that time who would have said, yes, this has to be done. This was nothing. You needed seed money of 100 crores, I was saying. Well, I was young, 50 crores they could have given and set up one center for quantum technologies in the country. And 50 crores was a good amount of money 20 years ago to do this. Anyway, what I mean to say is we still have that problem. still now with the mission even in place, that kind of a thinking among the people who control all the science in the country is not yet there. It is still taking time. That's why maybe the launching of the mission and unfolding of the programs under the mission is also taking time. The 2 years we have taken, even after having decided to launch it. 2 years is a long time.
I have just. So this 2000 event was a one unique event which had been Mysore event. So you were there, Simon were there, most of the people who started. Did you expect this type of growth in the quantum technology or other thing at that point of time? Because this was a young meeting happened in Mysore. And
no, it was expected. I think people knew. I mean, I at least spoke to so many people, spoke to so many people. This other meeting I'm talking about the nano mission and some money being put aside for quantum technology in year 2000 were organized in NIAS. And that was DST people also were around. So it is not that people did not think that this is. It was not that the people thought this is going nowhere and therefore people knew that quantum technologies are going to come. There was no that kind of a doubt. Because if you see, I mean, the whole work with the gravity detectors and putting in quantum ideas was also going very strong in those years. I mean, in the beginning, in those years, 95 to 2005, this whole squeezing ideas and putting them into Mach Center interferometers for gravity detection also was warming up.
Something to that, but not from the 2000 meeting perspective, because of course I missed it, right? But then, so I think what we always need is, few more success stories to happen in other countries so that we can get finally convinced that we should do it. And so in 2000, perhaps we didn't have that many, but now we have neighboring countries who are succeeding very, handsomely. And so I would just like to take an example of satellite QKD. So at least we have been trying to convince people who need the convincing that we should do this from 2013, right? And so 2016, we had a launch of the Mischius satellite from a neighboring country. And then in a brainstorming meeting, we've had many brainstorming meetings. I mean, of course, 2000 may have been the first one, but I mean, I don't have much brain left actually because of the number of brainstorming meetings we have had leading to this mission. And so in one of those meetings in Delhi, the director of the institute which was hosting this said that ये कैसे हुआ कि उन्होंने कर लिया हम लोग क्यों नहीं कर रहे so of course the answer to that is करना चाह रहे थे पर उन्होंने किया अभी करेंगे शायद नहीं. So then my project was approved within few months. So I mean, so I think we need these little pushes, right? To we definitely don't get very inspired to start something which doesn't have a lot of already success stories elsewhere. I think this is what I feel as a much younger colleague to Arvind, of course. But having said that, I'm sure you share the same sentiment, right? So yeah, just wanted to add that.
I should take up one thing which you mentioned is about the collaborations, right? This is something which lacks. When our neighboring country, when you said like, so it's not one group, it's a team which build that. And here we are looked down. Like, so when I did my first work on how to read out a single spin, electron spin, it was with the UK team. And some of the people who are guiding this quantum thing for the past decade or so in the country actually asked me how much of it is done here in India. Right? I had to say that the idea is from me. I didn't had a clean room to build this device. I had to go there and take it, write it as a project, Indo-UK project, and I did it there. No, not good enough. Like it's not done in India. This is, I don't know, this is very narrow vision and we should come out of that.
Maybe I'm getting more
Yeah.
comments and questions.
Yeah, maybe for questions from the audience. Students. You had the guy in the pink shirt. You had a question in the session, no? We forgot
Possibly, I'll take one more minute and I just say that one thing I said about the metrology. Vijay has mentioned about 99% is high-end electronics. This is something where we have huge opportunity. What we are developing and in our labs, I mean, just look at it. Like, so you can buy a lock-in amplifier, but if it is a NIST certified lock-in amplifier, you pay 10 times more. The NPL India is the NIST equivalent of, NIST US equivalent in India. We can do it here, but then when I say this, like, it's like I want to grab. So people actually ask, like, so how much money will you charge? No, we're not interested in taking money. We're not interested. We want to quantify, we want to qualify, we want to say that, like, certify that this is a good machine with certain capabilities. But once that is done by a National Metrology Institute, that's accepted the world over. If NIST says this is a NIST certified equipment, that's it. Like, so that's a standard. Right? So we can come together, whatever simple, whatever you think is a small piece of development can be made into a standard and standard equipment. And that can be sold at n factor higher cost, right? with quality issue.
Yes. So.
Thank you. So first of all, thank you for all the to all the panel members for an insightful session. So actually, jumping off of what recently was mentioned, I have a question based on looking at in quantum, especially when we're looking at gate-based technology as well as analog computing, we have various different ways of performing those computations. Now, when we're looking at from algorithms point of view, how do you guys propose that we perform benchmarking across different types of architecture, whether in gate-based or in analog computing, such that we can start kind of making some form of a standard between whether an algorithm is performing better or what types of algorithms are performing better for what specific type of computing quantum computing architecture?
Anyone?
Yeah. So, I mean, algorithms is not my core expertise, but see, today, none of the machines actually perform to ideal specs, which is, you might have heard the term NISQ, which stands for noisy intermediate scale quantum, which means small number of qubits, all noisy, which means they're unstable. Essentially, what it means is that your algorithm is trying to evolve the quantum state in a deterministic fashion in some direction, and the environmental noise and the decoherence processes is inducing some random changes. So after some characteristic time, you'd have no idea what the quantum state is, so the answer cannot be trusted. There is definitely some research which is happening where some kinds of algorithms might be more robust to those errors. And this requires understanding of the particular drawbacks in a particular architecture. So in one architecture, a certain kind of a gate might be very expensive in terms of how much error it introduces versus another one. So if your algorithm can be somehow tweaked to not use those gates as much and use some other gates which are more precisely implementable, then you can do better. One thing which IBM has been pushing a lot, and there was a very recent result also, is that for certain kinds of problems, even though your computer is making mistakes, if you understand the nature of those errors and you study it by actually artificially enhancing the same type of errors, but now making it more intense, and you see how the answer degrades, you can actually go back and find out what the answer would have been if there was no noise, which is the ideal case. Now, this is not universally applicable, but for some kind of problems, these techniques can be used, and they call it error mitigation. And they really think that because very recently, as opposed to 5 years ago when the whole NISQ thing started, people were really hoping that by having lots of people use these NISQ computers, maybe someone will invent a clever algorithm which will actually be useful. And here by useful, I mean doing something better than what we already can. Okay, not from just the point of I've solved a research problem, it's interesting on it. And so IBM, I think now thinks, at least from their papers and all, it looks like they're saying that error mitigation might be a way to get to something where you can use today's not so perfect computers to actually carry out an exercise and do something better than what is possible. As examples of what are possible in quantum computing and all of these experiments are valid. They just don't, they're not yet, there's not a strong case to replace or for industry to pick up and say, okay, for this process now I'm going to use a quantum computer. So that's there. And there are many such specific examples. It becomes now very particular to the kind of technology you're using, whether by changing the algorithm, you can do something better. And on a more general level, there are certain physical systems which are more naturally suited for analog simulations like cold atoms, because you can trap a lot of them very coherently and very in a controllable fashion, as opposed to trying to do that in a superconducting quantum computer where each qubit is not even identical, right? So some hardware-specific advantages do come in. And I think as we go forward, we will see that each technology will try to solve the problem which is most adapted to their features. And that's, I think, how we will make progress. And then there's also a possibility of combining different architectures together to achieve some goals.
I just wanted to add a few more points to what Vijay already said. So this analog quantum computation is, from my point of view, is more suitable for things like quantum chemistry and drug design and things like that. And even there are these new concepts of hybrid quantum computing which are coming into it in the picture. So you have a high performance standard classical computing cluster, and then you offload a small portion of that, the most difficult portion, onto this, take back your answer and do the remaining part of it. So that's a kind of hybrid approach which also might help in actually using these computers, the quantum computers, the analog quantum computers, in a more effective manner.
So yeah, I just add a couple of points that in terms of the circuit design, I think there are two approaches that one can achieve some particular task, so which is possible in classical domain, and for achieving the task, we have to see that when we actually cross the quantum supremacy. So that's the ultimate goal of it. And the second thing is that you can also increase the efficiency. It is not only enough that you achieve the same task, you can also kind of enhance the efficiency of the task. So in terms of, say, machine learning cases, you will be looking at the speed up of the process and speed up for a given amount of data. And also, you can also increase the domain of applicability that comes under the efficiency part. So both the aspects will rely on the optimization of the circuit and as well as error corrections, like already mentioned. And there will be a definite protocol is required for controlling decoherence and all these stuff. So, yeah.
Okay. Yeah. So this Vijay, for example, you were saying 3 to 7 qubits generalizations and other things. I have this question in the sense that what was the ultimate goal of this type of quantum computational experimental setups? Why I mean to ask this question is, for example, the industry, as far the industry is moving, the rate at which the industry number of qubits are moving, how do you compare that with the academic experimentations? So what is the ultimate reach? Are we going to technology usable by some people, or is it just an academic exercise where we can exercise?
Okay, thanks for that question. I'll also connect this to something Professor Deshmukh actually asked, that one only learns by making the mistake, or one learns better when you make the mistakes yourselves. If you actually look at, even in the international scenario, let's just, superconducting qubits is sort of in the news. Who has developed the 400 qubit processor? Not an academic group. In same way, Google's 53 qubit is also a record. I think the academic groups have not tried to demonstrate more than maybe, 10, 15, something like that. The question of why we are doing this is because there is nobody else to do it. I have for many years before I accepted this project, kept denying such requests because of this thing I mentioned during my 8 minutes, is that these are not suitable to be executed in an academic environment, because building a 5-qubit system is something that's already been done. Okay, now I can deliberately try to innovate and do something, touch my ear like this. And actually that's what we are doing because we had no other option left. The 7-qubit system we are building right now uses a very strange architecture which no one has used. It is not a scalable architecture, but we wanted to get the expertise of putting together a system, solving all the various problems, which includes device fabrication, the microwave architecture, putting together the electronics. And for this, we have been helped by our, the DRDO scientists who are also part of this project. That was the understanding that, the lab will still be set up in our academic setting, but we will have help from DRDO engineers and also from TCS on various aspects, and we can share the load accordingly. The pandemic messed everything up because we couldn't meet, but that was the idea. So right now, the 7-qubit quantum computer, once it's built, it's a toy. Nobody can use it to do anything useful. Your laptop will do a better job than this 7-qubit quantum computer. But till you get your hands dirty in doing that, you cannot plan a 50 or 1,000-qubit quantum computer. And this is something we have actually faced a challenge during our discussions at the time of writing DPR also, is that why are you saying that in 5 years you'll only build a 50-qubit quantum computer when Google has already done that 2 years ago? And we have had lots of challenges trying to explain this over and over again. And it is that unless you build 5, you're not going to know how to go about. There is no book available in some market which gives you step-by-step instructions on how to put together a 50-qubit quantum computer. These details are not published in papers, right? You only get an overall picture of what is happening. So even though I have been in this field for 20 years now, I started my PhD in 2001 in superconducting qubits, I don't know all the steps. So unless we spend time and make the mistakes, and then we realize, okay, now we understand why that person has used this particular idea. Now we know, and maybe we can do it better by doing something different. So currently, this is just a technology demonstration project. It's not going to be useful. It's partly to get the experience, partly it will be publicity that we have a quantum computer. And just like what IBM did 5 years, 6 years ago now, when they put their 5-qubit quantum computer on the cloud. I mean, my first initial reaction was, I was like smiling, said, what, really? Because your laptop would do better. If you talk about practical usage, a laptop will accurately simulate a 5-qubit system, whereas this very expensive machine will very poorly perform a 5-qubit system. But what it did is that it, I think, helped a much larger community realize that, oh, these machines actually do exist and you can play with it. And then slowly, of course, as the number of qubits becomes larger, even putting that together is non-trivial. And IBM has made, and including Google, has made lots of technological advances to go from 5 qubits up to 433 qubits right now. But some people will still claim that they're still using the same technology. They're just keeping on pushing on the boundary and they have not done something groundbreaking yet. And those groundbreaking discoveries might be needed to really take this from a barely working technology to something which really, really works. And there are other groups and other companies also now coming up which are trying to do that. So that's really the thing. You have to start. Now, the problem is, where is the equivalent of IBM or Google in India, which is willing to invest their own money to do that? And that's actually going to be a challenge. So we have to do, and we have to do it by moving slightly away from academia, while having the academic people involved, because the core expertise is still concentrated, unfortunately, only in academic groups. But there are lots of very talented engineers in government labs, and maybe with some companies, we can work together to develop the electronics and some of the other peripheral technology. And then you will have a large enough ecosystem, and maybe some company will be willing to invest and take it forward in that large scale. But we need to find those people. So, and all that happens when there is a thriving research ecosystem for 20 years. And the industry says, okay, now there is a lot of scientists, they have done the basic research, there are many students who have been trained, we can hire them, put them in a company, in an industrial setting, give the funding and do it at the fast pace. That is missing, right? So we have that challenge. We have to do this together, but somebody has to do it. And because in every field, there's only one or two or three obvious suspects, we get called upon to execute those things. So that's the answer, I would say.
Thank you. Thank you.
Actually, half of the question Arvind asked, the thing which I want to know, see, unlike the other countries where we are looking, this quantum mission is going on much. This quantum mission is going on much higher success rate. How we can motivate our younger generation for this, where we see so much disparity between academia and industry as in our country? I think part of question you answered, but I think this will be a great challenge. We see a good decline in the people who are now interested in coming forward, taking research in leading technology.
Right. Okay, I'll just give one example. Like, so the quantum computing is one, quantum communication is the other one. We need detectors. If you look at quantum communication, but those detectors, the same silicon APDs, array of them, have multiple applications. Now we're in talk with some medical application. Can we build our own? MRI has been built in the country, first time. Right. Now we're talking about next generation, scanners with low, radiation detection capabilities and other things. So it's not just, we may be focusing on one particular technology, but the spin-offs will be a lot more. The technologies which will be generating within the country or have a lot more applications and wider consequences than just having a 5-qubit computer or a 7-qubit quantum computer. What the technologies which are developing will have a lot more applications and a lot more capabilities which will take us forward than without having that knowledge. Right? Yeah,
I would like to add to his question about the motivation of students getting lost. I think I disagree with that a little bit, because as long as we do our job of reaching out to the students, having facilities to show them on what is going on, what is happening in this field, I think students are quite motivated and they want to join these particular research programs. I think it is our responsibility to kind of increase these activities, put enough money, increase these activities, have good research programs and labs running in our institutes, having good outreach programs, public talks, lectures, etc. Like you think of a program which is analogous to what astrophysicists do. I mean, you go to any school or college, you will find almost 80 to 90% of the time students talking about their interest in astrophysics and cosmology and all, right? Something like that, this community also has to do within this particular domain.
So I kind of agree, and I would just add one point from my experience when I was in Wiseman. So that time I realized that students from 10th standard or equivalent standards, they are coming. I was working on ion traps, and our job as a lab member was to explain them that. And I don't see any such program, at least to my knowledge, where such an early stage people are being exposed to. Maybe they may not understand the company.
This is surprising.
This happens in many places.
Each institute has different thing. Like, so there are many institutes. Most of the institutes have open days and science days.
We have a science activity day, for a science activity center, for example. Yeah. Every weekend there are bus loads of students who come, and then some small activities happen, and once in a while, once in a week or something, they are taken on a campus tour, some lab tour or something. I think that is
talking in a relative terms as a size of country. I'm talking in a relative terms.
Just each one will contribute, right? TFR has excellent science outreach program. NPL itself does, we cater to about 186 schools across Delhi NCR. Every year we cater to about 10,000 school students minimum.
Okay, this is one part of the mission also. I mean, it has to be part of that quantum mission also. The outreach.
Outreach should be
There is
there.
no question that this has to be scaled up by, again, orders of magnitude to really get to the state. But there's also, so all of these things are connected. If you talk about being exposed to cutting edge research in cutting edge labs, they didn't exist 20 years ago in most areas, right? I mean, as India has grown as an economic powerhouse in the last 20 plus years, all of these things are connected to that. The fact that we're talking about a 6,000 crore mission today is connected to, I mean, you could say that, okay, somebody could have been very visionary and decided that this was very important and decided it 20 years ago. It's not such an easy call, you know. The government also has to balance various things. There are others, various problems. You know, how much flack we got for spending money in our space program internationally. But, you know, there was a vision and that has happened. So these are all connected and you have to take the scale of this to a different level. And that will happen as more such labs happen. The industry will also emerge from that as well. We just have to make sure that we keep pushing it and not, you know, doing a half job of it and then essentially letting it fail. That's the most important thing, that we keep up the momentum. I think somebody earlier had mentioned that we need some long-term commitment on this kind of thing. It's easier said than done, but right people should keep pushing for it. I mean, people like Arvind should go to every forum and say that, you know, we need to keep doing it. He started 20 years ago, but I think he needs to keep doing this. And then I think, you know, maybe in another 20, 30 years, we will be in a different situation. These things cannot change overnight. We have a unique opportunity now, and we have to try and do our best by getting all of these things. Suddenly you want like the perfect system out of something which doesn't exist. And that's going to be hard. We have to understand our limitations, but try to do the best within the circumstances. But at the same time, you know, I have now started saying this in many of these open domain. It's fantastic that the government has decided to invest in this very important technology. But I also want to request the government and the other, you know, concerned people to make it easier for us to exploit these resources to actually do the job. And, you know, this has come up in various discussions during the lunchtime as well. There are too many things which are unnecessarily wasted. I mean, this is like, you know, you give the best batting gear and everything, and then you put yourself on a muddy.
Tapping resources is not easy at all.
Yeah, but I want to come back to the question which was raised, because I think it's a fundamental question. Let's not shove it under the carpet. This is nothing to do with quantum mission, or for that matter, in any domain. Is the talent in the country going in that direction in which it can excel? Answer is no. Partly, well, we are sitting in an IIT, partly this whole idea that to do well, you must pass certain specific competition exams, only then you can do well, and then only you are talented. This has to be, you know, changed. So data says that about 90% of the students in our country don't really get opportunities to explore their talent. So there is so much latent talent in the country which has to be tapped. Now, talent could be, you know, in quantum technology, or the talent could be in linguistics, or, I mean, for that matter, in any domain of activity. We are not channelizing the talent into where it can flourish. So that needs to be addressed at the country level, and then that would be my answer to your question. I mean, look at medicine. Are we really looking at skills to be a good doctor, to become a doctor? No, we are saying you pass some test, and then if you pass the test, you can become a doctor. But that test typically has nothing to do with your abilities to become a good doctor. Same is true of an engineer, and same is true of science also to a great extent. But maybe less in science, because science is not so economically attractive. So many people who have intrinsic interest in science end up coming into science at the end of the day, because, you know, stakes are not so high. But we need to change this scenario. And we also need to build a certain confidence in the younger generation that anything you excel, you can do well in it. You don't have to choose one over two, three careers to do well. This is where, see, we have a system, a society which basically runs on insecurities. So quickly you want to go here or here or here. Otherwise, people say you will be either jobless, you will perish, this, that. But that is not true. So we need to change that mindset.
It's happening. It is happening. It's just not happening fast enough for us to. Yeah, actually, very exciting ideas have come out of this discussion. And one thing that appealed to me very much is that building a quantum computer involves a lot of classical engineering. And if we popularize this idea, make students in schools know this, that they can be a part of this very exciting journey. Otherwise, they think that only Google and IBM, this is not for me or for anybody I know. But we have to let them know that they can be a part of it. They can contribute to it in a very big way. So
we have started some workshops on bringing industry together, specifically to explore only this classical engineering, classical technology, instrumentation technology,
yes,
and other things for building anything related to quantum technology. Well, they will be useful for other things also.
Sure, of course.
It will, what it will also do is it will reduce import burden.
Yes.
We don't have to go buy SRS lock-in
Yeah.
amplifier, for example. Every time we need a lock-in amplifier.
Yeah. Is there any other question, comment? Arijit?
Yes. As was highlighted by one of the panel members, that for the mission to succeed, collaboration will be a key element, right? And not just national level collaboration, but also international level collaboration. So my limited experience while doing my PhD in India and then going outside for doing postdoc was that I have seen people outside India much more open. So two labs who are fiercely competitive, but they are still very open about sharing knowledge and resources. That's what I've seen outside India. But in India, what I've seen is people somehow live in their own shell and they hesitate to talk to each other. Even neighboring labs don't interact with each other. So how do we overcome this inertia of this intrinsic hesitation to talk to people and to collaborate with people across India, because it's a national mission, right? And probably for this to succeed, not only the IITs and IISERs would also probably need the universities to play a big role in this mission, right? So how do you think can we achieve this? Or is the DPR or the people or the powers that be, have they put a thought on this issue?
I think we need to start at some point. This is one of those points where we're coming together and talking to each other, right? Unless we know each other, we'll not going to come and discuss openly what our ideas are. I think we need to keep meeting together often and then find the same frequency band with people, and then that's how the collaborations will evolve. It's not that like everybody outside is talking to everybody around. The collaborations have to be built, and I hope like that's what we need to keep working on.
Yeah, there are certain cultural transformations which I think you are hinting at, which are very much called for, I would say. When people realize that, okay, their competition is only with themselves, and the only way you can do better than yourself is to make your opponent stronger and then try to do something better than him. So that is something which is very common in many of the groups that you were referring to. And I'm sure it will grow in India as well. Urvashi can add.
Yeah. Just wanted to add, because of course I raised that point initially as well. I think why we have this problem is because we are not secure about ourselves. So we are not particularly confident that we are indeed doing things the way they should be done. And so we are insecure about discussing with others, because then we believe that our lack of knowledge is going to come through. I think that is one of the reasons why we are not, as collaborative. So we need to be more comfortable in our own shoes and realize that, if it is collaborative, also to ensure that in a collaboration, we know what is our individual role. I mean, so that nobody feels less or more in some sense. So, I took the example, which was an obvious one, that, there is a memory, then there is the transfer, and then, so people have their individual contributions, which will make the whole thing succeed. Without one, it's not going to succeed. So these are the kind of projects in which this can start, where, it is going to happen only because of all these elements coming together. Then we will go to a stage where, we will be happy to talk to our neighbors. I like your example very much, that we talk about things to people several thousand kilometers away, but we don't really tap the next door. And that is hopefully going to change, but I agree that this is how it is, right? It's not fiction. Yeah.
Yeah,
So,
I think we have had a very exciting session, and as we ponder over everything that has been said, many more questions will come, but we will save them for future interactions. You can communicate with the experts or by email or whatever. And I'm sure that they will be very happy to respond to your queries or comments and respond to this. May I request Professor Satyanarayana to make a few comments?
I just want to use this opportunity to talk about a few issues, which came up during the discussion here. First thing is just, we have the Technology Innovation Hub on positioning and precision technologies here at IIT Tirupati. So those initiatives, and we are talking about creating the industrial capacity in the country, creating the startups and so on. So if there are technologies at TRL 4 or so and above that need to be supported in the PNT area, positioning, navigation, and timing area, I think we'll be glad to look at those and see how we could support those, since we have the TIH here with reasonable funding that is available, and we're still looking for how to deploy these funds into these initiatives. The second point is, again, saying people are not talking to each other, people this. So a lot of times people say, I went to this lab, they used to do all that there. Then I keep asking my colleagues, why are you not doing it here? Right? What's stopping you from doing some of these things here, right? Keep telling that it happens there. Okay, you come here with the experience, and then why don't we do things here? But they'll say that this, right? But I think a lot of things we just put constraints against ourselves. But more importantly, the getting kids excited about science and getting into science. I think a lot more outreach needs to be done. And since we are in the state of Andhra Pradesh now, and we're talking to the schools department, right? The schools department has come to us and said that we would like to run a program for the science teachers to do a better job of teaching science. And let's start off with the 8th to 10th class teachers. So then we said, okay, IIT and IISER will do it together. So we're working with them on, getting teachers excited, themselves excited before they can excite the kids, right? Very often, unless they're excited, they're not going to excite the kids. And we have a challenge here in AP in the sense that, and I quote this in so many different places, that I was told that 85% of the kids who go to +2 do a science-based +2. 85% in AP. Apparently, national-wide, it is 35%. In Andhra Pradesh, it's 85%. But then how many go on to do science? Almost negligible. Okay. You take IIT, if you take IIT, IIT Tirupati, the students who get into a BTech program, 65% of them are from AP and Telangana, Telugu speaking, 65. Across all IITs, because I did the survey on behalf of the Ministry of Education, about 17% of the students are Telugu speaking, okay, across all the IITs. The second largest, the highest they said was 52, because I did an extensive survey for the thing, 52% are Hindi, claim they're Hindi speaking. The next biggest linguist group is Telugu speaking, 17%. Next one is Marathi, some 7 or 8%. And then the rest of them, Tamil, Malayalam, all these are only 3-4% of the students who get into IIT are other things. But the point is, which means that so many of them are getting to IIT. Professor, you may want to start looking at the statistics of the students who are coming into your program. They say, at least 3 years back or 4 years back, IIT Tirupati admitted 104 students, about 4 years back. I'm looking at it, talking, which I collected at that time. 4 students are from Andhra Pradesh. Okay, out of the 104 students. In my institute, out of the 240 students, 150 students are probably 130, 140 students are from Andhra Pradesh and Telangana, Telugu speaking. So there is this, that means the students are capable, they have this thing, they're able to get into IIT, they can also get into IISER if they have the inclination, but they're not ready to go into science. This thing to go only into medicine or in yeah, that year when I collected that data, because I was talking to the chief minister and others, and I had taken this data, and I was surprised. Out of them, 40 out of the 104, then now of course they're admitting more. I think the percentage increased a little bit better, maybe from 4% it's gone up to 6% something, but it's still negligible. 40 or so from Kerala, right? Some 30 are from West Bengal, and then maybe some 10 or 12 from Maharashtra and the rest from the other states, right? So this penetration of people, I'll give you another example. Dr. Vengama, who was the vice chancellor of SWIMS, the premier medical university in this area. She's a doctor, her whole family is full of doctors, right? Her son was passionate about going for science. And then the whole family was, how can you send this fellow to study science, right? We're all doctors. And so she came, met me, she met Ganesh saying, my son is passionate. He went to NICER, but I think he's now in Bangalore. He went and studied biology. But she had to fight the family so much to let her son, she's the vice chancellor of the main medical university here, okay, to get her son to study science. Okay, the guy was passionate. Of course, she's a thing, she could do it, but not a regular family. So point I'm trying to make is, I think there needs to be a lot more effort in educating the parents first. The biggest problem, 80-90% of the problem is the parents, where they don't let their kids go after their passion. And I think that point was alluded to here, that also by someone, about people going after their passion. But more importantly, I look at this room today. I was sitting here and looking at it. I said, they have this, we say the top people in quantum are here. We want to get kids to come and join our program. To all my colleagues here, why didn't we use this opportunity to bring in some people doing BSc in physics and other things here? Say the best, each college identify some 4 or 5 good colleges and said, come bring them over here. You can interact with the top people in this particular area, right? And this is all for your long-term interest in terms of getting people excited and getting them to come and join join our master's programs and the physics program. So I'm saying, we keep talking, we're Institute of, national importance, global, local relevance. So I think there's a lot of things to be done by ourselves.
Even your BTech students would have benefited.
Yeah, exactly. Yeah, Dave, yesterday, what is that area where we had one student came and told me, I'm going and doing a quantum course in IIT Madras. Is there anyone in IIT Tirupati who can help me in quantum? I said, go meet Arvinda, go meet all these guys. Now, where are those kids? Now, our students are going and and when you bring, so somewhere we are not communicating well. The point I'm trying to make is we're not using this opportunity to communicate well within our institute, within the ecosystem around, and get them, saying in Weizmann, they used to bring school kids. What's preventing us from bringing school kids into our labs and putting them there? Of course, you'll say you didn't you give me money to do all that. I think if you want to do it, we'll find a way, right? If Weizmann can do it, you've seen the thing, why can't we do it here, right? So these are things I think we need to, but I'm very concerned about this, not enough students coming to PhD. It's not only here, in all areas, right? We've seen a big dip in the number of PhD applications. And I was in a meeting with just 3-4 days back with Ranga, ISC director, and all these people, a lot of other directors from IITs, and everyone has seen a dip in PhD applicants. Right now, it's a challenge for us, and of course, the whole problem is the CS kind of everyone just clamoring to get into CS kind of programs. Again, another statistic. Many of these big private engineering colleges, SRMs, VITs, and so on, they're having 25-30 sections for computer science. They admitted something like 6,000 students in the undergraduate program, out of which 5,000 plus are for computer science variations, computer science and engineering, computer science and data science, computer science and AML, computer science and cybersecurity. Then they will say computer science and engineering and all this various, computer science and technology and all these variations, information technology and something and all these variations and so on. Anyway, there is a big disruption that has happened especially last 4-5 years. This is going to be a challenge. And no students have, even being an engineering person, students are not joining civil engineering, mechanical engineering, even electrical engineering is seeing a dip. Everyone is just clamoring for computer science. But I think it's and on the side, there was this studies coming out with this AI, ML, all this chat GPT and all this, half these jobs are going to disappear. And, but more importantly, I think the science-based people need to do a little more outreach, need to get more people excited about it. And since this point came up, I thought I'll use the opportunity because this is something I've been talking about in various forums. Thank you.
Yeah. Shall we conclude the session, Arvind? Rajat? Yeah. So thank you all very much. We have had a very exciting session, and I just want to mention one thing before I invite Sambuddha or Shavani to propose a formal vote of thanks for the gathering. That whereas the center is run by Arijit and Sunil, we also get a lot of help from the chairman of the Department of Physics at IISER. Now it is Prasenjit has recently taken over, but earlier it was Professor Ambika and Arunima for some time. And over here at IIT, Ritesh and Dr. Koteshwar, who was the first head of the department, and both of them have played a very big role. And also other colleagues, Vinay, and some of them are not here, but very grateful to all of them. So, Shavani?
Can I just?
Yes.
In my 8 minutes, I didn't want to say anything other than what I wanted to say. So thanks to you for organizing such a session. I think it is first such session which is not, formal in some forum and all that, where within an academic institution, there is such a panel discussion has been organized. So you have pioneered it and maybe many more will come.
Thank you very much for coming.
I'll just thanks. So just to conclude that we have very nice, about 3 months of all these talks and this session. So I'll start by thanking the people who bring the CAMOST into existence, like Professor P.C. Deshmukh, the two directors at that time, Professor Satyan and Professor K.N. Ganesh, and our current director, Professor Bhattacharya, and all the chairs, our ex and present chairs of currently position, previously Ambika Urnima, and here earlier Koteshwar and currently Ritesh, and I just thank all of them for bringing this. And Arijit and Sunil, who are the main people who does all the heavy lifting for running all these things. And I'll finally thank all the panel members here. The discussion was really interesting, and we wish it was longer, and we should do it more. But it has to end at some point, and so that's all. I'll just thank finally all the support members, like all the people who were arranging all the behind the scene people from the office and all the staffs. And with that, I thank everyone, all the participants. And there will be a tea coffee session, T plus delta T as we call it, right outside. Okay, thanks.
It's okay.
Okay.
Can be left here, they are for the pictures.